Okay, hi, we're starting a new unit on electrostatics, which means static electricity. You've probably experienced static electricity if you ever went down the plastic slide at Memorial Park. Probably you got a shock the next time you touch something metal. Or if you rub a balloon with your hair, you might be able to get it to stick to the wall. Or if you ever take your laundry out of the dryer in the dark, especially if you've got something wool in there and it's stuck to some other laundry and you pull it apart, you might see sparks in the dark. That's all static electricity. What I expect you to already know about static electricity is that most things are neutral. So actually, we don't think of it as a really strong force because we don't experience a lot of electric force, but actually, it's way stronger than gravitational force. If you think about how you could um, get a balloon to stick to the wall with a little bit of static electricity, that's overcoming the entire gravitational force of the entire Earth, right? Which is a huge mass. And this little bit of static electricity is stronger than that. So, yeah, electric force is really strong, but you need to have more positive or more negative charge there to have a force. Otherwise, if it's neutral, things are going to kind of balance out. So you could have, if you have the same amount of positive as negative, that's neutral. Um, and you should know that like charges repel. Positives repel positives, negatives repel negatives, opposite charges attract. And you should also know that protons and neutrons are located in the nucleus of the atom. So this is kind of the current model of the atom, that the protons and neutrons are all in the center. Protons are positively charged, neutrons are neutral, and the electrons are kind of in this cloud around the nucleus, and they're negative. And if you have more of one or the other, or less of one or the other, like if you lose some electrons or gain some electrons, then you have a net charge. Okay, now remember when we talked about fields? When we got into gravity, we talked a lot about how if an object has mass, it's going to interact in a gravitational field. And so a field is something in space that uh, that causes forces on objects that have the right interacting quantity. In the case of gravitational field, it's mass. Um, and the field is shaped by interacting objects that affect the field, like masses, like the mass of the Earth causes a change in the gravitational field strength around the Earth. Okay, so um, I want to make the distinction between properties that describe an object and properties that describe space. So force, you could talk about the force acting on an object. You could talk about the energy that an object has, right? Like gravitational force or gravitational potential energy is the property of something. But fields and potential are properties of space itself. There doesn't have to be an object there for that space to have a field. So let's review. Why don't you answer these two questions? Pause the video, and then I'm going to come back and tell you the answers. Pause it now. Okay, so the field we studied is gravitational. The field strength of gravitational field is little g. And the interacting quantity is mass. The force is gravitational force, Fg equals m times g. And so if we look at a gravitational field, I'm doing this because I want you to understand electric fields, but this is a good way to understand it. We have the interacting quantity, we have vectors showing the direction of the force on any mass in this field, and these rings represent levels of potential energy, gravitational potential energy, and you can notice that the force vectors point from higher potential levels to lower potential levels. You could think about this gravitational field as a hill where some object up at the top of this hill is going to go to lower and lower and lower potential, gravitational potential. And that's because it's experiencing a force in the direction of from high potential to low potential. Okay, the electric field is very similar. It has an interacting quantity, but it's charge. So the charge can be positive or negative, which is a little bit different. And the vectors show which direction is the force. But the question is, what charge is it that we're talking about the force on? What charge is this vector representing? Pause the video and answer that question. Okay, hopefully you realize that these arrows are showing the direction a positive charge would go, and so are these arrows. In fact, force vectors in an electric field always show, electric field force vectors always show the direction a positive charge would go. Sometimes we talk about a positive test charge where there's actually no charge there, but we just want to know which way would it go so that we can map out the field. And these rings represent levels of potential in an electric field, which we call voltage. So if you've heard the word voltage, that's what it means. It's potential levels like gravitational potential, but now electric potential called voltage. And you notice that the force lines always point from higher potential to lower potential. So the negative charge has the lower potential, the positive charge has the higher potential, and the lines point away from positive and toward negative. Okay, so let's go back to the gravitational potential example so that we can really understand this for electric stuff. You're familiar with this, you know, if there's a soccer ball here, it's going to feel a gravitational force down towards the Earth. That's Fg. And it's going to have gravitational potential energy. Now we're talking about properties of the object. That's the object. Now let's talk about properties of this point in space with no soccer ball anymore. It's just a point in space. Is there a field there? Yeah, because if you put an object there, there would be a force on it down. So the gravitational field at that point is down. And it has a potential. It's not really a voltage. We call this would be gravitational potential, which we don't talk about potential as much as potential energy, but it's basically the same idea, except potential is the potential energy with the mass divided out, because it doesn't depend on mass. Just like little g is the force with the mass divided out. So instead of being mg, it's just g. And this is, instead of being mgh, it's just gh. And I'm going to summarize all of this in a minute, but I just want you to see these things. See if you can follow along here. Okay, let's make the electric analogy. Here's a charge. This is a positive charge, and it's experiencing a force from a big plate of negative charge. The force is towards the negative, down, so it's experiencing electrical force, Fe, and electrical potential energy at that distance from the negative plate. The more you pull it up away from the negative plate, the more potential energy it has to, when you let go, fall down towards the negative plate, just like the soccer ball. Those are the properties of the object. Now let's look at the properties of the field with no object there at all. There's still a field, and the field lines point down because they always point the direction a positive charge would go. The field strength is the force divided by charge, and the potential or voltage is the potential energy divided by charge. Same idea as with gravity. Okay, so just to summarize, when we talk about an electric field, we're talking about something that fills space, just like a gravitational field. There's some kind of force at every point in space, and if there isn't, that's part of the field too. You can map it out, right? And every charge in the whole universe contributes to the value of that field and could be affected by the field also. It's an abstract mathematical quantity used to determine the force on some object from other charges that are causing this field. All right, so there's a handout. You could, if you want to print this from the link on the assignment sheet, you can, or you can just copy this stuff on the handout, but I'm going to summarize everything on this handout for you. First of all, I want you to see that all the gravitational quantities have electric analog quantities. So if you see mass in a gravitational equation, just replace it with charge Q in the electric equation and you get the same, you'll get the correct electric equation. If you see big M for big mass, okay, big Q. If you see little g, gravitational field strength, that's E, electric field strength. If you see the force of gravity, that's electric force. If you see the gravitational constant, that's Coulomb's constant. By the way, this is really small and this is really big. That tells you something about how much stronger the electric force is. If you see electric potential energy, or sorry, gravitational potential energy, that's going to become electric potential energy. And if you see gravitational potential, which we haven't talked about before, but I'm making this analogy so you can see what it is, so you can see what this one is, this is voltage. Okay, here's a grand summary of the whole idea, and the top is all gravitational, the bottom is all electric, and everything parallels each other. The first big box is forces and energies, or things affecting an object. The second big box is no object needed, just whatever the field is in that location. Okay, so here we have gravitational force or gravitational force between two objects at a certain distance apart. And here's the gravitational constant. Here we have electric force. It's Q times E, just like this is M times G. And here's the force between two charges at a certain distance apart. And there's the constant K, which you can see is really large, while this one's really small. Then we have energy. So gravitational potential energy, as you know, it's mgh. Well, the electric analog, if you replace m with q, g with e, h with distance, you get QED. That's electric potential energy. Okay, now let's talk about fields. So little g is gravitational field strength, just like E, or F over Q, this was F over M, is electric field strength. Or we had little g is gm over r squared. Similarly, E equals kq over r squared. And then finally, potential. So I told you gravitational potential is when you divide out the mass, so it's just g times h. Well, electric potential is the analog of that. It's the field strength times the distance. And so V, voltage, equals electric field strength times distance. Okay, I also want to mention units. You know, mass units are kilograms, charge units are coulombs. And the other thing is the force in gravity is always going to be in the direction of the gravitational field. See that? But for electric fields, if the field is down, that's just the direction of force would be on a positive charge. So positive would have a force down, but a negative charge would have a force up in that same electric field. Okay, see if you can do this problem. Here you go. It's a force problem. Free body diagram. Write your givens, write your unknowns. Pause the video. See if you can solve this problem. Okay, I hope you took time to try to solve the problem yourself first, because now this will be a lot more meaningful to you. But here's the free body diagram of this charged object. The forces on it are a force up and force down. We know there must be a force up because this is a balanced situation and it's got gravity pulling it down. So we know the electric force must be pushing it up, which means since this is a positive charge, the electric field lines or arrows, vectors, must be pointing up. Here are the givens. Here's the equation. Solve for the electric force and then solve for the electric field strength. And it's upward. And you can see that newtons per coulomb is joules. That's the definition. Newtons per coulomb is joules. All right, and there's your example for today. And that's all. Okay, try your homework, and I'll tell you about the lab next time.